Welcome everyone to another segment of introductory lectures where we were discussing about coordinate systems in general, and in the last lecture we saw the cyclic behavior. So we saw the cyclic behavior of the basis vectors, the cyclic behavior of the contravariant and basis vectors. So we will continue from here in this lecture and develop the general ideas of writing the various vector operators like the grad, the divergence, and the Laplacian in a general fashion in any coordinate system. Let's say so we are developing the idea from a generic coordinate system perspective, where we started with basis vectors in an arbitrary curvilinear coordinate in in 3 dimensions. Okay, so let's see. So remember where we had this expression where we had grad of, let's say, this could be represented as a sum over I equals 1 to 3 ei at by the scale factor hi partial phi partial ui. Okay, so let's use this important identity that we developed, and using this let's try to find out what that if phi is the ith curvilinear coordinate. Let's say, remember this ith curvilinear coordinate, like we had u1 u2 u3 in 3 space. Okay, and we were thinking about u1 equals to c1, the surface in that 3-dimensional space. Okay, so let's say if phi equals ui, what will this equation become? So this equation will become grad phi. Instead of phi we have ui, and this will become ei at by hi, where if we substitute phi equal to ui, the sum will only survive for the component where phi is ui. So the cross terms will not be there, because like the derivative of, let's say, u1 with respect to u2 will be 0, because u1 and u2 are orthogonal and they're independent coordinates. Okay, so grad of ui will become ei hat by hi. Hi is the scale factor. Okay, so the magnitude of grad of ui is the magnitude of ei hat by hi. Okay, so then this becomes since this is a unit vector, so this becomes 1 over hi. So this is a very important expression that we got, and you see this relates somehow the contravariant components with the covariant components. Okay, because if you see the right hand side, e sub I, this represents the contravariant components, but the grad ui, this is the normal component, so this represents the covariant basis. Okay, so let's keep in mind this this identity. This will become very handy as we develop further ideas. Okay, so let's now what do we have? Let's say we want to write the divergence operator. Okay, so let's say we write divergence of, say, a1 e1 vector. Okay, so if you see this, we can write using, so let's say we use this middle expression. Okay, if we use this middle expression, we can write e1 as e2 cross product e3. Okay, and then using this expression which we just now derived, where we had ei hat is hi grad ui, so this we can rewrite as h2 grad u2 cross h3 grad u3. Okay, so this becomes, so this is e1 cap. So therefore the E1 vector becomes H2, H3. So these are the scale factors in H2 and H3 multiplied by grad of U2 cross product grad of U3. Okay, so that's what E1 is. Okay, and let's use this E1 and let's substitute it here to expand the divergence. So this will become the divergence of E1 cap. This is equal to the divergence of E1 H2 H3 grad U2 cross grad U3. Okay, and remember this identity is this we had. So similar identities we can write for the other directions. So we can write, let's say, E2 is H3 H1 grad U3 cross grad U1, just using the cycling nature of 1 2 3. And similarly for E3 we can write E3 equals H1 H2 grad U1 cross grad U2. Okay, so let's see now. So let's remember a vector identity which we know from before. Vector identity, which is basically the equivalent of kind of the product rule of calculus. So let's say we have the divergence of a scalar function, let's say y times another vector, let's say b. Okay, so phi is a scalar and b is a vector. Okay, so this becomes, remember, so this is like the product rule, so it's like the grad phi dot b, okay, plus phi divergence of b. Okay, so if we use this identity, for A1 E1, where we recognize that what is phi and what is b. Okay, so if you see phi, like so if we compare, let's say, phi b, we identify that phi, if we represent phi by this term, which is A1 H2 H3, and the b vector by the cross product of grad U2 cross grad U3. So recognizing this is phi and b and using this vector identity, we can rewrite the divergence of A1 E1 cap. So that is the divergence of E1 H2 H3 grad U2 cross grad U3. That's what we had before, and now using the rule of this vector identity, recognizing appropriately what is phi and what is b, we can expand this as the grad of A1 H2 H3 dot product with grad U2 cross grad U3 plus A1 H2 H3, the divergence of this vector, so this is grad U2 cross grad U3. Okay, and now realizing what this can be. So this is like the divergence of curl of something. You can think about it like that. It's not strictly like that, but we can think about it in this direction, and we can show that this will be equal to 0. Okay, so then this expression becomes the grad of E1 H2 H3 dot and grad of u2 we can using this identity we can write as E2 by H2. That can be written like E2 by H2 using the contravariant components instead of the covariant. This will be written as E3 by H3. Okay. So finally this could be written as the grad of A1 H2 H3 and E2 cross E3, that is E1 divided by H2 H3. Okay, so just like this we can write the other components basically. Okay, but before writing that, let's expand this thing even further. So remember the grad operator. The grad operator is defined using this del operator acting. So this is the grad acting on a scalar function. So this is the sum over I equals 1 to 3 ei by hi. So using that we can expand this basically. We can expand that, and that becomes E1 by H1 partial U1 A1 H2 H3, and we have a sum, so over three components. So E2 by H2 partial U2 A1 H2 H3, and then plus E3 over H3 partial U3 A1 H2 H3, and this entire thing dot product with E1 H2 H3. So if you see, we are just dotting it with E1, so that is the only component which will survive. So this is the thing that will survive, the others will become 0. So the orthogonality of E vectors, E1, E2 and E3 conditions. So then this will become divergence, or let's say divergence of A1 E1 cap. This is equal to, you see H2 H3 and H1 is down, so it will become 1 over H1 H2 H3, and then this will become partial with respect to U1, and this will become A1 H2 H3. Okay, so this is H3. Okay. Similar expressions we can have for, let's say, the other components. So let's say you have A2 E2, and just using the cyclic nature of things we can write it like H1 H2 H3, and this will be partial U2, and this will become A2, and you see the cycle 1 2 3, so this will have the cycle 2 3 1 H3 H1. Okay, and similarly we can write divergence of A3 E3, which is 1 over H1 H2 H3, and then this will become partial U3, and this will become A3 E3, and instead of, so that will become H1 H2. Okay, so that's the divergence of A1 E1 cap, A2 E2 cap, and A3 E3 cap. And now identifying, like we can write the vector A in the contravariant basis, like A1 E1 cap plus A2 E2 cap plus A3 E3 cap. We can take all the things together to find out the divergence of the vector field in an arbitrary curvilinear coordinates with scale factor H1 H2 H3 as this. So this is H1 H2 H3, and then we will have is a sum basically. So as you can see, it will become partial U1 a1 h2 h3 plus partial u2 a2 h3 h1 plus partial u3 a3 h1 h2. Okay, so this is the general expression for the divergence of a vector written in an arbitrary curvilinear coordinate system. Okay, with where we realize h1 h2 h3 as the appropriate scale factors in the 1 2 3 direction respectively. Okay, so this is the expression that we were targeting to have, and this is a very general expression, as you'll see, and this expression we'll see use it for various coordinate systems to get the expressions for the divergence operator in the corresponding coordinate system. Okay, so now if in this expression, let's say if we substitute instead of a, if we substitute grad of any scalar, let's say, that means, so yeah, what we have in my mind is that ai is basically, remember from partial phi partial ui, the ith component of the, so this is what we are talking about, grad of phi. Okay, so that's the component. So if we recognize this, that ai is this, this is the gradient of phi. So yeah, so this is the thing that we're thinking about. Okay, this expression basically, if you see, so here instead of f we have a 1 over hi. Yeah, so that is the idea that we are thinking. So if we substitute a is equal to grad phi, you see the left hand side becomes the divergence of the gradient of phi. So this becomes the Laplacian operator del square phi, or that can be written as, this is the Laplacian of phi. So we can have a general expression for the Laplacian of any scalar field. So the general expression for the Laplacian of a scalar field is given by, just becomes 1 over h1 h2 h3. It naturally follows from this expression which we had, and this will become partial u1, and instead of a1 we will have 1 over h1, you see, 1 over h1 partial phi partial u1 basically. So we will have h2 h3, which are these two things, and then we have one h1 from here, and then we will have partial phi partial u1. Okay, and like that for all the other, we just substitute a's i's appropriately here. So this will become partial with respect to u2, and this is h3 h1 by h2 partial phi partial u2, and plus partial with respect to u3, and this is h1 h2 by h3 partial phi partial u3. Okay, so that's what we have as a general expression for the Laplacian. So we have written the general expression for the divergence, and we have written the general expression for the Laplacian of a scalar field. Okay, so the divergence of a vector and the Laplacian of a scalar field in arbitrary curvilinear coordinates. Okay. So that this is these two expressions are very powerful, and as you'll see, the only thing that we require to get to a specific form is knowing what are the scale factors. Okay, so if we know what are h1 h2 and h3, we can get the specific expression for the individual coordinate system. Okay, so that's the power of this this method, that and the generalization that we were trying to build. So now we have these two expressions, and using these we can write the divergence of a vector field and the Laplacian of a vector field in arbitrary coordinate systems. Okay, so we can write the divergence and the Laplacian in a particular coordinate system. Okay, in a specific coordinate system, and that's what we will be doing now in seeing the specific cases. Okay, so So before that, like, let's write what is the volume element. The volume element in the orthogonal curvilinear coordinates that we used. Curvilinear coordinates, okay, and that is, I think that's given by h1 du1, h2 du2, h3 du3. Okay, that's the volume element. Okay, so let's, so this if we compare this with the volume element in each coordinate which we had before, we will be able to figure out what h1, h2 and h3 are in general. Okay, and another thing to why these two expressions are so powerful is this is a looks very long, but this is a very simple. There is a pattern to it. If you see, like h1, h2, h3, and then partial with respect to u1, a1, and then 1 2 3 2 3 1 3 1 2. The cyclic nature is there, so that makes it very easy to like keep this thing in mind. Okay, so let's say, for example, in Cartesian coordinates, we realized what was the volume element. So the volume element dv was dx, dy, dz. Okay, and from, if you recall this, we can rewrite like this. So where we realize the individual h1, h2, h3, the scale factors all are 1. Okay, so h1, h2, h3 all are 1. Okay, and just if you substitute h1, h2, h3 all equal to 1, you will see the divergence of the vector as well as the Laplacian. We will get to the familiar fields, where the familiar Cartesian expressions. Okay, so let's do another case where, let's say, in cylindrical coordinates. What is the volume element? Let's write the volume element. So dv is, in cylindrical coordinate, is dr into rdr, or no, so it's, if you remember, this is dr into rd theta. That is proper. This was dr into rd theta, so that was in the azimuthal direction, and times dz. Okay, and if we compare this now with this expression, we will see that h1 is 1, since what we are doing is h1, we are realizing h1 du1 is basically dr, where we recognize u1 is r, and the factor that sits in front of dr is 1, so h1 is 1. Okay, similarly, we will get h1 is 1, h2 is r, and h3 is 1. So if we use the values of h1, h2, h3 in these two expressions, we will get the appropriate expression for the divergence as well as the Laplacian. Okay, so let me write the Laplacian operator in cylindrical coordinates. So that will become 1 over r, because remember, you have 1 over h1, h2, h3, and if you see, h1 and h3 is 1 and h2 is r, so the product is r, and this becomes del r of r del phi del r. Okay, you see, because that is h2 h3 by h1, and since h2 is r, this r comes from that h2, plus del theta 1 over r del phi del theta, plus del z r del phi del z. Okay, and if we now just open the brackets, we will have Laplacian of the scalar field phi in cylindrical coordinates is given by 1 over r del r partial phi partial r, plus 1 over r square del to phi del theta 2, plus del to phi del z square. Okay, so that's the Laplacian in cylindrical coordinate systems. Okay, similarly we can write it for spherical polar coordinates. Let us do that. So let's write it for spherical polar coordinates. In spherical polar coordinates, let's identify what was the volume element. So if you recall, the volume element dv was dr into rd theta into r sine theta d phi, where now this was the azimuthal term, this was a zenith term, and this was the radial term. Okay, and if with this we recognize with h1 du1, h2 du2, h3 du3, we realize that h1 is 1, h2 is r, and h3 is r sine theta. Okay, and if we use these h1, h2, h3, we can show that we will just substitute h1, h2, h3 in this equation, and out pops the Laplacian of a scalar field in spherical polar coordinates. Okay, so this will become 1 over r square sine theta del r of r square sine theta del phi del r plus del theta. So make it, because we are using also phi for a coordinate variable, so let's use capital phi as the function. Prevent any confusion. So that will have del theta of sine theta phi del theta plus del phi 1 over sine theta 1 over sine theta del phi del theta. This is phi. So this will become square of phi is 1 over r square del r of r square del phi del r plus 1 over r square sine theta del theta of sine theta del phi theta plus 1 over r square sine square theta, and this will be del 2 phi del phi 2. So that's Laplacian in spherical polar coordinates. Okay, so we saw how to get each of the Laplacian operators in cylindrical as well as spherical polar using the general expression that we derived, and same thing can be done for the divergence. Okay, so that's what we wanted to show. A general way of writing these two expressions are the things that we wanted to understand, and then we wanted to show how general these two expressions are for the divergence as well as the Laplacian of a vector and a scalar respectively in arbitrary curvilinear coordinate systems. Okay, so that's for this segment, and we will see you in the next segment with some other materials. Okay, so thank you.